So we're starting Unit 5, and the first section is on this mean value theorem, it's called. We're going to split the unit up. There are, I want to say, 13 sections to Unit 5. So we're going to split it at 7. So our next test is after the Section 5-7, just so you know. So first one, here we go, mean value theorem. When you think of mean and you think of math, it's probably a loaded question. What word should pop into your head when you're thinking mean? Because we've done a lot of mean problems, that's for sure. But yeah, average is what you got going on. So what they're really looking for is what an average value would be. Now, you know average values, we just talked about them. They're a lot like slope, right? So if I'm finding the average value, the average rate of change, then I'm finding like a slope. So we use that, they call it the MVT, the mean value theorem, MVT. Kind of like the IVT. We're going to bring up the IVT in this section too. And here's what they say. We use the MVT to justify conclusions about a function over an interval. So if a function is continuous over the interval, now you know intervals go, right, A to B with closed brackets, and differentiable between A and B, then there exists a point C. They didn't leave us much room for these little things, but C, within that open interval where the instantaneous rate of change equals the average rate of change over the interval. So in other words, they're saying this: my instantaneous rate of change, I'm going to use ROC, equals the average rate of change. So if I'm looking at it, if I'm thinking about it, the instantaneous rate of change is the actual derivative. So I know that f prime of C, the derivative at C, is equal to the average rate of change. Well, the average rate of change is the slope. So that's your f of B minus f of A over B minus A. And so I'll give you a picture so you can kind of get the gist of what they're talking about. You've got some kind of function. Here it is. And you have a point A and you have a point B. Right? So in between there, you can see that you've got a continuous function. It's going to have a derivative, and so I can see that if I were to connect these two, I'm going to change up some colors here. If I were to connect these two together, these points, do you remember what kind of line that's called when it connects like that and it connects through there at two different points? This guy here is called the secant line. And if I want to know the slope of that secant line, that's just going to be my f of B minus f of A over B minus A, right? The slope of that secant line. That's like my average rate of change. But at some point in here, I'm also going to have, do I have or can I have a value C? I'm going to put it down here. My value C, where I have a tangent line. This guy here's my tangent line. That has the same exact slope. And this would be my value that's C. Because if I look at these two lines, they're parallel to one another. They're going to have the same slope. So that the instantaneous rate of change at C is equal to the average rate of change for your secant line. And that's what this is saying. So that's the theory behind where we're at with this loveliness. So it says in number 1, use the function, yada yada, to answer the following. On the interval from 2 to 6, what's the average rate of change? Well, as soon as you see an average rate of change, you're thinking slope. So we want to know what f of 6 is minus f of 2 over 6 minus 2. So I plug it in and I figure it out. Don't let this negative get you. Remember, that's separate from, you have to square first and then apply the negative. So be careful with that guy. But put a 6 in here. So I've got 6 squared is 36. So that's a negative 36. Plus 3 times 6 is 18. And then plus 10. Minus. Plug a 2 in. 2 squared is 4. It's going to be a negative 4. Put a 2 in, you get 6 and 10. Plus 6 plus 10. All over 4. All right, so you work out the details. I'll give you a second. Tell me what it comes out to be. Toss me an answer in the chat when you get to it. I am in agreement with my girlfriend Sydney. It's negative 5. All right, so the second part, B, says, on the interval from 2 to 6, when does the instantaneous rate of change equal the average rate of change? Well, you just figured out the average rate of change. If I want to figure out the instantaneous rate of change, instantaneous means find me the derivative. So I need to go back to my function and find the derivative. So I need to know what f prime of x is. That's going to be a negative 2x plus 3. So the question is, when does that negative 2x plus 3 equal the average rate of change of negative 5? And then it's just a matter of solving out. So I got negative 2x equals negative 8, and x is 4. And there you go. So all of this is kind of stuff you already know, in a sense. The mean value theorem versus the intermediate value theorem, the derivative or the instantaneous rate of change must equal the average rate of change somewhere in the interval. So that's the mean value theorem. That's the first one here. And then the intermediate value theorem we've seen before. The intermediate value theorem said that in a given interval, you'll have a y value at each of the endpoints of an interval, and every y value exists between the two y values at least once in the interval. So it's like it's got to be continuous, and we've used that as a reasoning for some of our justifications in some of the problems earlier that we've done. So is the answer an x equals, or is it at a point? Most times they leave it as an x equals, not as a coordinate. Could you find the coordinate? Absolutely you could. You would take that 4 and plug it back into the original function and figure out what that value would be. Would it be wrong to use a coordinate instead of just using an x equal? Absolutely not. So if you're more comfortable putting it as a coordinate, you can, but really for this they're just looking for what the x equals for these values. Watch the wording, because they could sometimes ask for the coordinate. They could say, you know, yeah, what's the coordinate? But for this, if they're not clarifying it or specifically asking for a coordinate, the x equals 4 is sufficient for an answer. All right, so we're flipping. I'll try some more. It's actually only one more example problem, and then we get into some practice problems. So here comes number 2. A hot air balloon is launched into the air with a human pilot. Okay. The twice differentiable function h models the balloon's height, measured in feet at time t, measured in minutes. The table above gives values of h of t and the vertical velocity v of t of the balloon at selected times. So for 5 to 20, between 5 and 20, must there be a time t when the balloon is 50 feet in the air? All right, where am I here? 5 to 20. So I'm looking at this part of the chart. I don't care about the 0 end and I don't care about the 30 end. I'm looking between 5 and 20. And I want to know if this thing ever is going to hit 50. So if I look at my values here, remember the intermediate value theorem? If I go from a 40 to a 70 to a 65, will I ever cross through a 50? And I have to, right? Because they said it was a differentiable function, meaning it's continuous. You know that it's got to cross through. So we're going to say yes to this because oh, here's the other thing that I thought about on the test. You don't ever want to use it as referring to the function. You want to literally call it f of x, because Mr. AP, when they're reading the exam, they don't know what it is. They don't know what you mean by it, but they do know what you mean when you say f of x. So you need to be specific on that as you're answering your justifications for these. So yes, because maybe I should just say because h of t goes from, really it's just the 40 to 70 and must cross through 50. By the IVT, by the intermediate value theorem, right? That's the one that says it has to hit everything in between. Okay. So there's your part A. Part B, for 20 to 30 for your t, must there be time t when the balloon's velocity is 1.5 feet per second? Well, that gets a little bit trickier, right? So between 20 and 30. So I'm looking, here's my 20 to 30 range over here for part B. Must there be a time t when the balloon's velocity is 1.5 feet per second? We can't just generally say the same thing, right? Because now I'm going from 2 to 4 for my velocity. So this is going to take me a little bit more work to figure out if that's really true. And so what you're going to do is this is what they're giving you here is the instantaneous rate of change is 1.5. So you want to check to see, remember the mean value theorem says that the instantaneous rate of change has to equal the average rate of change. So your job is to figure out, well, what's the average rate of change and is it equal to that or not? So I want to find an average rate of change, and that's going to be my f of b minus f of a over b minus a. So I've got f of 30 minus f of 20 over 30 minus 20. So I go to my chart and I check it out. So f of, or h, I guess they were using h of 30 is 80, h of 20 is 65, and then I have 30 minus 20 is 10. So I end up with 15 over 10, which is 1.5. Does that actually equal your instantaneous rate of change? And it does. And so therefore you are saying yes, because the average rate of change equals the instantaneous rate of change by the mean value theorem. Okay. We'll do a couple practice problems. I picked a few random ones. Number 3 was my first choice. Here is number 3. So again, a hot air balloon, right? So similar question to what we just were doing. This one, this one's slightly, I mean, I guess our process is very similar to what we just did with that last one, but the answers will be just a tad different. So this one, the hot air balloon is launched, human pilot, twice differentiable function. Differentiable means continuous. Models of balloon's height, measured in feet, at time t, measured in minutes. Table below gives values of h of t and the vertical velocity v of t for selected times of t. So for 6 to 10, now 6 to 10 is only these two, right? You're only looking at those two this time. So if I'm looking at 6 to 10, must there be a time when the balloon is 50 feet in the air? Well, look at your heights. Your heights are 46 and 35. So I'm connecting between 46 and 35, and I can only tell what it's doing between those two values. I can't tell what it's doing outside of that. So this one they want to know at 50. 50 is not going to work. 50 is not between 46 and 35. So we say no. We could add on, since they want us to justify, the intermediate value theorem shows has it. Oh, I just did the it. Let me go back and fix that, right? Shows h of t has values between 46 and 35. $50 is not. What's a good word? I'm not thinking. 50 is not. It ain't part of it. Included. Yeah. Okay. I like that. Thank you. Thanks. See, help me out. Yeah. Good. Okay. So for part B, for 10 to 40 seconds, must there be a time when the balloon's velocity is 3 feet per second? Now this is the same thing we just were talking about. This is the instantaneous. This is my instantaneous rate of change. I need to justify and see what the average rate of change would be. Question here. Wait, isn't this the one where it's like it could though? Yes, but there's no guarantee. That's the deal. So Sid, the way that the IVT works is it could spike up and go through 50 and come back, but you have no guarantee that it does that. All you know is that it goes from 46 to 35. But could it? Yes. Can you guarantee it? No. And so that's the deal with this. The intermediate value theorem is a guarantee. You guarantee that it's got to hit that place. And in this case, there's no guarantee. So you're right, it could. Right, you would just say that, yes, you would just say there's no, you would say there's no guarantee that it goes through 50. However you want to word that or whatever. It's yeah, it's a possibility it could, but you can't prove it. You could if it were like, say it were, I don't know, 40. If they asked you what it was doing at 40, you'd say, yep, absolutely, it's going to go through there. But in this case, because it's 50, you don't know for sure. See, there's no guarantee with it. All right, so we're going to look for the average rate of change to see if it equals the instantaneous rate of change for this guy. So I'm doing h of 40 minus h of 10 over 40 minus 10. And so you go and you check it out here. I've got 105 minus 35 over 30, or 70 over 30, or 7 over 3. And so I'm looking, and these are not the same thing. And so that means that the mean value theorem does not apply. But this one's tricky, because this one, you actually can answer the question a different way. So what you want to do, and I'm going to change my color here so you can see the difference here. You want to check if this doesn't apply. Like in the other one, the other example that we did, it applied and you were done and you were good to go. If it doesn't apply, you want to check the intermediate value theorem of the velocity. All right, so what do I mean by that? You want to take this thing and look at your velocity things. Look at your velocities in here. Oh, this is between 10 and 40, by the way. It is this set down here. So these are the ones that I'm looking at. So if I look at the velocities, they go from 20 to 1. Will they hit 3? And they will. So the answer actually, if I check my intermediate value theorem of the velocity, and that's looking at it going from 20 to 1, velocity will hit 3. Velocity will equal 3 by the intermediate value theorem. So go back to your question. Must there be a t when the balloon's velocity is 3 feet per second? And the ultimate answer is yes. The mean value theorem didn't apply, but if I go back and I look at the velocities, they're going from 20 to 1. I'm going to absolutely have to hit a 3 in there by the intermediate value theorem. Good call, John. Why did they say feet per minute when they asked you about feet per second? And they made a mistake for sure. So I guess we should fix them. This should be minute. Did they do that at the top? No. Yeah, good call on that. They would never be that mean where they're going to end up giving you the wrong things and on purpose, if you know what I mean, wrong units on purpose. All right, got that one? So it's a little different. Did they do it in the other one too? Silly kids. See, you're smarter than them. You got it. They can't fool you. All right, number 5. Use the mean value theorem, find where the instantaneous rate of change is equivalent to the average rate of change. All right, so these are the guys where you're going to find the, number 5 is the next one. And I picked this one because I know how much you love the trig. So here it is. You need to know what f prime of x is, and you need to set that equal to your average rate of change, f of b minus f of a over b minus a. That's the goal for these questions. Find where the instantaneous rate of change equals the average rate of change. So you put it in. We can find our derivative, and it doesn't matter what order you do these in, but if I figure out the derivative first, derivative of sine is cosine of the angle 3x times the derivative of the angle is a 3. So I'm going to put that in front, 3 cosine of 3x. All right, then I'm going to f of b minus f of a this thing. So I've got f of pi minus f of 0 over pi minus 0. Now that's going back and putting it in the original. And so if I do that, if I put it back in the original, that's the sine of 3 pi minus the sine of 0, 3 times 0, over pi minus 0 is pi. Now think about 3 pi. 3 pi, if I go around my unit circle, lands on the same place as pi. The coordinate there is -1, 0. And the sign is the y value, so it's 0. If I'm at 0, then the coordinate is 1, 0. Sign is the y value, that's a 0. And so you end up with 0 minus 0 over pi, gives you a whole lot of 0. Did you catch all that? I mean, I know you have your charts and things. Oh, which by the way, that too reminds me that if you are in school taking the AP exam, all bets are off with reference sheets and things. So all of these trig tables and such that you've been leaning on, you're not going to be able to use. So maybe we'll have to have a couple quizzes on the unit circle or something to get that fresh back in your head. They do not have any reference sheets. No, it's a good question. Yeah, no, they have nothing. They give you a whole lot of nothing. So a lot of things they want you to have in your head. So we'll work on that between now and then. But all right, so here's where you're at. You've got to take your derivative, set it equal to your average rate of change. So here's where I'm at, and this is where I thought this might be something that you haven't seen for a bit. I want to solve that for x. So the first thing I'm going to do is divide by 3. So that's going to give me the cosine of 3x. 0 divided by 3 is 0. And then you say to yourself, well, I don't know. Where does the cosine of 3x equal 0? So what you need to do is think about the places where the cosine is 0. So cosine is the x value. So if I'm thinking unit circle, the x value is 0 here and here, right? On my unit circle. That's where the x's would be 0. Well, this is pi over 2. This is 3 pi over 2. And so well, that's what you're going to do. You're going to set 3x equals pi over 2. 3x equals 3 pi over 2. And because this is a 3, you're going to do one more time. If I were to come around here one more time, this no longer would be, if I do a whole nother full circle and come back to pi over 2, can you think about where you'd be? You know what I'm talking about? If I went around, got to pi over 2, kept going around, got to pi over 2 a second time, it'd be pi over 2 plus a whole another circle. So it'd be 5 pi over 2. You'll see why I did this extra one in just a second. You want to know what x is. So how do you get rid of the 3 that's in front? You're going to divide by 3, multiply by 1/3. Maybe that's an easier thought. Multiply by 1/3 gives me pi over 6. Multiply by 1/3 gives me pi over 2. And multiply by 1/3 gives me 5 pi over 6. These are your 3 answers for this question. And if I go back here, look at what your domain was between 0 and pi. And so you want to make sure your values are between 0 and pi. And you can see how this extra one that I did comes in being less than pi. So you actually have a value there. And it's because this was a 3 in front, you're going to have to go around the circle more than one time to be able to get all your answers. Otherwise, you'd be missing this whole piece here that actually is a valid answer. There's number 5. All right, here comes the next one, number 6. Questions before we flip the page? I thought the algebra of number 6 was a little bit tricky. So here it is. You've got same question. So you need to find the derivative, and you need to find the average rate of change, and you need to set them equal to one another. All right, so here's what I've got. I'm going to look for my derivative first, y prime. Well, power comes down in front, right? So I've got 1/2. The grouping -5x plus 15 goes to 1 less power, so -1/2, times what's the derivative of what's inside, and -5. Well, let me see if I can make that any better. I know it's a fraction because I've got a negative power here. So in the denominator, I have a 2. Here's my 2, this guy. I have this square root, negative 5x plus 15. And I have a negative 5 in the top, this negative 5. It's just a regular whole number. So there's my derivative. All right, let's figure out what f of 3 is minus f of 1 over 3 minus 1. If I put a 3 in here, I get negative 15 plus 15, so I've got 0. If I put a 1 in here, I get 10 to the 1/2, so I've got the square root of 10 over 2. So I have negative square root of 10 over 2. And then the deal is I have to set those two things equal to one another. So let's see where that goes. I have a negative 5 over 2 square roots of negative 5x plus 15 equals a negative square root of 10 over 2. So the first thing that I can do is and I'm going to put it out here in a different color, what I'm going to do algebra wise, I can multiply both sides by a negative 2. If I multiply by a negative 2 on either side, that gets rid of the negative and it gets rid of the 2's. And so what I have next is negative 5, actually positive 5 over 2 is gone, square root of negative 5x plus 15 equals the square root of 10. All right, and then the question is, how on earth would you go about solving that? That's kind of algebra that we haven't seen for a while. But as soon as you see the square roots, maybe try squaring both sides. Square both sides. That's what we're going to do. So square of 5, you get 25. Square the square root, you get rid of the root. Square the 10. Square the square root of 10, and you get 10. And then that puts it without all that ugliness in there. So just take the 10, put it over 1, cross multiply, and that's where we're going to go. I have 25 equals negative 50x plus 150. I can swing that 150 over. That makes this negative 125 is negative 50x, and then divide. And it goes in 2.5 times, and there you go. So some algebra in there I wasn't so sure that you would remember how to do. Okie doke. There were a couple test prep questions that I thought might be difficult too. I'm watching our time, and I don't think we're going to get to section 5.2, but 5.2 is very short and sweet, so we can save that for later. But let's finish these last couple test preps that I thought might be difficult. Number 10 and number 12, and then we'll call it a day. So let G be a continuous function. The graph of the piecewise linear function G prime, the derivative, of G is shown between negative 4 and 4. Find the average rate of change of the derivative on the interval from negative 4 to 4. Does the mean value theorem apply on that interval? Guarantee a value for C such that the second derivative at C is equal to the average rate of change, y or y not. So this is the graph of the derivative G prime. Well, the question is, does the mean value theorem apply? So they want to know, does g prime of negative 4 minus g prime of 4 over negative 4 minus 4, actually negative 4 minus, yeah, I think that's good. Oh, maybe not. Other way around, right? 4 minus a negative 4. That's better. 4 minus a negative 4. B minus A. That is true. That's going to come up in a minute there, Ms. Sid. You are correct. So they want to know if I mean, I can go through and apply the mean value theorem. Sid's ahead of me on this, and she's right. So if I put this in, I get f of 4. I did the same thing in the numerator. Silly me. It's f of 4, or g prime of 4 minus g prime of negative 4. Gives you a negative 2 minus 2 up top and an 8 on the bottom. So I end up with a negative 1/2 ultimately. So yeah, can you find a value where is there an average value there? And the answer is yeah, you can find one, but the problem is no, because this doesn't apply. Is there a guarantee of a C value for this? You can't. This is a pointy graph. This is not a smooth sailing graph like the other ones have been. So the answer to this is no, because is there a value of C? And you say no, because g prime of x is not differentiable. So the mean value theorem only applies if the function's differentiable. That's really what you're looking for here. No, because g prime of x is not differentiable. MVT only applies to differentiable functions. There it is. So really, did you have to find this in the first place? The answer is no. But it's interesting that you can find it and you can get a value, but the answer is still no, doesn't work, because you're not looking at a differentiable function there. So this, because of the pointy places in it. And then here comes the last one. This one's a calculator guy. I don't know if you have your calculators handy, but we can kind of look at it. Let f be a function given by 2 sine of x as shown above. The graph f crosses at the origin at point A and point B at the coordinate pi over 2, 2. Find the x coordinate of the point on the graph of f between A and B at which the line tangent to the graph is parallel to the line AB. And then round. So this is kind of like the picture we looked at in the very front when we very first were talking today, that I can find a secant line through the 2 points. That's my f of B minus f of A deal. And that should have the same value as what the tangent line would have. So that's what I'm going to work on, is figuring out what f of pi over 2 minus f of 0 would be, because they only want it from pi over 2. So pi over 2 and 0. And then I've got pi over 2 minus 0. Well, f of pi over 2 is 2. It's my y-coordinate right here. F of 0 is 0. And pi over 2 minus 0 is pi over 2. So here's where I'm at. I've got 2 over pi over 2. If I think about that, that's like 2 divided by pi over 2, or 2 times 2 over pi, or 4 over pi. Now, if I look at that, then I want to compare, I want to set, this is my average rate of change. What's the instantaneous rate of change? And that's go back to your function and figure out the derivative, f prime of x. So 2 is a coefficient, just keep in there. The derivative of sine is cosine, and they had it just as an x. And so what you want to know is where that happens, where these two things are equal to one another. So you're going to take your calculator in the solve menu of your calculator, and you're going to take 2 cosine of x equals 4 over pi. And you're going to let your calculator do the work for you. And then you get an answer, I'll tell you, 0.8806. All right, there you go, my friends. That is section 5.1. Now we'll go for... is anybody opposed to me teaching the section 5.2 on Wednesday?